In this video and maybe the next, I want to derive the standard error for beta hat 1, and I'm going to do it by going through and solving or proving each of these hold. So this is where this was our equation from where we last left off, talking about beta hat 1, and we got this equation by starting with the idea that OLS minimizes the squared residuals, the sum of the squared residuals, and then we took first order conditions, and that's how we got this formula for beta hat 1. I want to show number 2 holds right now. So I'll start with number 1, and I'll show that number 2 is a result. So say this, and I'll say I want to show this. So my first step is I'm going to, so notice beta 1 is in this equation and beta 1 is not in this equation. So I need to find a way to introduce beta 1 here. Of course, beta 1 is the true relationship between x and y. Beta 1 hat is our estimate. So the way I'm going to introduce beta 1 here is I'm going to use yi. Yi, the true data generating process, we assume, is beta naught plus beta 1 xi plus ui. So that'll help get beta 1 in the equation, along with ui, and we need both of those. And another thing I'm going to use is, so y bar, I'm just going to take the average of this. The average of beta naught is beta naught, it's a constant, plus beta 1, the average of beta 1 is a constant, and then the average of xi is x bar, average of ui is u bar. And of course, e bar is 0, but u bar is not necessarily 0. So making those substitutions, I'll have beta hat 1 is sum I xi, and then I'll write this, beta naught plus beta 1 xi plus ui minus x bar, sub in for y bar, beta naught plus beta 1 x bar plus u bar, and then I have an n here, all that divided by sum I xi squared minus x bar squared times n. Next, I want to separate this out. I want to separate the numerator into 3 parts. I want to separate the numerator into a part with beta naught, a part with beta 1, and a part with u. So here's my next step. Say beta hat 1 is, so my first part will have the beta naught in it. Beta naught sum I xi, and then we'll have this beta naught. So minus beta naught x bar n. I have this n over here at the end. So that's the part with beta naught in it. Divide by sum I xi squared minus x bar squared n. Then I want to focus on the part with beta 1 in it. So my first part is beta, I'll work on this. Beta 1 sum I xi squared minus, now this part, beta 1 x bar squared n, and then all that divided by the same denominator. And then I'll have a term with u in it. So plus sum I xi, working on this part, ui, minus x bar u bar n. And then also with that same denominator. And I'm going to see if I can move this over here. Great. Okay. Notice that what I want to show doesn't have a beta naught in it. I have to argue why this term goes to 0. And here's how I'll do it. Beta hat 1 is, as an aside, I'm going to write this useful fact. X bar is sum I xi divided by n. You add up all the x's and you divide by the total number. And so sum I xi is equal to x bar n. If you just multiply both sides of this equation here by n, you'll get this equation. So I'm going to use that here, right here. If I make the substitution for sum I xi, we get beta naught x bar n minus this term, beta naught x bar n divided by the denominator. And we get beta naught x bar n minus beta naught x bar n. This term goes to 0. So I'll just write 0 here. Plus, now let's work on this beta 1 term. Notice in the thing that I want to show here, beta 1 stands alone. So I have to argue that this term simplifies just to beta 1. So let's see how that holds. Let me take beta 1 out in front. I'll collect beta 1 outside of the two terms here. So I'll say beta 1 sum I xi squared minus x bar squared n divided by the denominator. The denominator, by the way, is sum I xi squared minus x bar squared n. Notice this term here is exactly the same as this term, and they cancel. So we're left just with beta 1, which is what we hoped would happen. And now let's look at the final term here. We have sum I xi ui minus x bar u bar n over the denominator. What do we want to show? We want to show it's equal to this. So let's see. Let me make this substitution for x bar. We know x bar is sum I xi over n. And then I'm going to make an argument for that the denominators are equal. So let's start with the numerator. Sum I xi ui minus sum I xi over n times u bar n. Oh, I did the wrong thing. Actually, I want this to be I want this to be talking about u bar. The average of the u's are if you sum up all the u's and divide by n. So, because we actually needed the x bar in here. So I'll say x bar sum I ui over n times n. The n's will cancel, and I'm left with just this. And what I want is this in the numerator. And we're really close. I can put them all under the same sum. So I want to work on the numerator here. I'm going to put them all under the same sum, and I get sum I xi ui minus x bar ui. There are parentheses there. And then I'll take ui out in front, xi minus x bar. And notice that is exactly what I wanted to show is equal. This and this. Okay, so that's our numerator. So I'll say beta hat 1 is beta 1 plus this thing divided by this thing. And we're so close to being finished, let's see, here's what we want to show. And I'm actually going to work on this to show that it's equal to this. If we take this and we FOIL it out, so we get sum I xi squared plus x bar squared minus 2 xi x bar. And then we use the fact that x bar is sum I xi over n. I think that'll help us. So we'll get, and then let's do, multiply the n over to this side and sub in here. Then we'll get sum I xi squared. I also want to break this up into 3 different summations. So instead of having it be one summation, I'm going to have it be 3 different ones. So here, this term just stays sum I xi squared, and then we say plus, and so I'd say sum I x bar squared, and that just means, so x bar is of course just a constant, and x bar squared is a constant. So if I said xi equals 1 to 10 of 3, that means we sum 3 10 times. So that's 3 plus 3 plus 3 10 times. So that'll be 30. So what is sum I x bar squared? We sum x bar squared n times. So this thing will be n x bar squared. And this is minus 2. I'm going to sub in for sum I xi. So that's n x bar times another x bar, so n x bar squared. So we have sum I xi squared plus something and minus 2 of that thing, which just comes down to minus 1 of that thing, which makes it equal to that. So we've shown what we wanted to show here. Beta hat 1 is equal to the true value of the relationship between x and y, beta 1, plus this term, which is a function of the data x, and the unobservable term.